I want to go through one more example of finding the radius and the interval of convergence, because a lot of these problems can look very different, and the work that you do can be slightly different depending on what the original series looks like. So we want to find the radius and interval of convergence. And this time we are going to do the sum from 0 to infinity of -1 to the k, x to the 2k, all over k factorial. We want the interval of convergence for that function, or for that power series. So it definitely does not look geometric because of the -1 to the k and the k factorial. So we're going to do the ratio test. So what they have given us is our a sub k, and we need to write out what a sub k plus 1 would be. So wherever I have a k, I'm going to put a k plus 1. And be very careful when you do this. X to the 2k does not turn into the 2k plus 1. It's 2 parentheses k plus 1. And then k plus 1 factorial in the bottom. And our ratio test says we want the limit as k approaches infinity of the absolute value of a sub k plus 1 over a sub k. The nice thing about the ratio test is those absolute values are going to allow us to just completely disregard the negative ones. So I'm going to write out what this would look like initially, and then we're going to do some simplifying. So just like the last one, instead of fraction divided by fraction, we're going to flip and multiply. But right away, because I have absolute values, we don't care about sign changes. And that's all the -1 does, is flip-flops our sign back and forth between positive and negative. And we can get rid of those right away because the absolute values. So we'll flip my denominator and turn this into a multiplication problem. And I wanted to do this one specifically because of the factorials. Factorial means that we're doing like repeated multiplication starting with the number that's listed. So k plus 1 factorial means k plus 1, and then we multiply it by every whole number less than k plus 1 all the way down to 1. So if I subtract 1 from that, I'll have k. Subtract 1 from that, I'll have k minus 1. And we just keep doing this until we get to 1. And since I don't know what k is right now, I'm just using some symbolic representation. K factorial is going to do the same thing, but it starts with k. And then 1 less would be k minus 1, and all the way down to 1. And you'll see that when you write out what the factorial actually means, that we've got a lot of matching factors between the factorials. So the k minus 1s and everything below that would cancel, since both of them are going all the way down to 1. The k's would cancel. Technically, all we would have left is a k plus 1 in the denominator when we simplified those factorials. Also with our x's, the top has 2k plus 2, the bottom has 2k. That means the top's always going to have 2 more. So we're able to simplify this down to limit as k approaches infinity of x squared over k plus 1. And as k approaches infinity, remember, if you want to, you can pull the x out, and since it's squared, we really don't need the absolute values with it, but that's the whole reason the absolute values are in this problem. K is only ever going to be positive if you look back at our original summation. K goes from 0 to infinity, so we don't ever have to worry about k being negative, but it is possible that x is negative. So this limit only has to do with the k's, and the limit as k approaches infinity of 1 over k plus 1 is equal to 0. So we get absolute value of x squared times 0, which is 0. So some people will get to this point and get really confused, because remember, we're trying to get this to look like absolute value of x minus c is less than r. But no matter what you get from doing that limit, remember, our ultimate goal is for this to be less than 1. We're doing the ratio test, and the ratio test says that our series will be convergent as long as that limit comes out to be less than 1. Well, we got 0. 0 is always less than 1, which means our radius is infinity, our interval is negative infinity to positive infinity. No matter what we plug in for x, that limit is always going to be 0, and 0 is always less than 1, which means this series is not convergent or divergent depending on the x value. The series is always convergent, not only on particular x values, but always. So we've got a radius of infinity, which means from our center of 0, and I know the center is 0 because I can look and see if there's anything being subtracted from my x. From the center of 0, we're allowed to go infinity to the left and infinity to the right. So we get negative infinity to positive infinity. We don't need to check those endpoints because infinities are not real numbers. It's just an idea that says we can continue getting smaller and smaller forever, or larger and larger forever, and we're never going to stop. Infinities always get parentheses anytime you include them in an interval, so we don't have to check. Okay, so that's another example. It's kind of tricky, but I wanted you to see one that had some factorials in it. I also wanted you to see what happened if that limit came out to be 0. So we're going to wrap up 9.2 with some properties. And these properties are going to allow us to bypass that whole Taylor polynomial process every single time we want a polynomial. Usually we just need a couple of very basic infinite series representations, and we can use those to generate a whole bunch of other ones. So suppose the sum of a sub k converges to f of x, and the sum of some b sub k's converges to g of x on some interval I. They of course would have some sort of interval of convergence that we have to be careful of. So we know just two polynomial infinite series representations here for two different functions f and g. There are lots of different things that we can do with this. The sum of a sub k plus the sum of the b sub k's, we could actually combine these and say it's the sum of a sub k plus b sub k, and this is going to converge to whatever f of x plus g of x is. That's going to give us a brand new function, f of x plus g of x, and we don't have to go through the whole Taylor polynomial process that we learned in 9.1 to figure it out. We can just add the two series together. And this actually also works for subtraction. So we could subtract those two series and get the difference of those two functions. So we can do a lot of addition and subtraction combinations to create new functions. Another thing that we can do is we can multiply by a power of x. So if I wanted to figure out a series for, let's say, x to the n times f of x, this is going to be equal to just the sum of a to the k times x to the n. As long as we're just doing a power, we can just multiply it in there. And I'll show you an example of this in a minute. So this works for multiplying by powers of x. Now you can't decide you want to multiply by a cosine or an e to the x. That won't work. It's only if it's x to a power. And the third thing we can do is composition. So I'm going to write my series a little bit more detailed here. Let's say we've got f of x is equal to the sum of c sub k times x to the k. Then f of any other function, I'm going to call it g of x, because it could just be replaced with a different linear function. So in x we could say 3x or x minus 1, but it works really for any type of function, not just linear functions. I can say f of square root x or f of sine x. We really wouldn't want to use sine though, because our goal here is to make a polynomial. So as long as g is algebraic, and that means it just involves addition, subtraction, multiplication, division, and powers. All I have to do is replace the x with g of x in my series. So I've got the sum of c sub k g of x to the k. And we saw this, a very simple example of this, back at the beginning of 9.2 when we were looking at geometric series. We had said if 1 over 1 minus x is the sum from k equals 0 to infinity of x to the k, then 1 over 1 minus 3x would be the sum from k equals 0 to infinity of 3x to the k. So that's a classic example of how the composition works. Whatever I want to replace in the function, I do the exact same thing in the power series. So if I replace x with 3x in the function, all I have to do is replace x with 3x in the power series. two more very convenient things that we are allowed to do with these power series are derivatives and antiderivatives. Taking a derivative or an antiderivative when it's in summation form can look confusing, but the best thing to remember is that x is the variable. Everything else is just going to be a number. So when you see the k's, those are just numbers. You don't have to think of them as variables, even though we see them as letters. So one more here we can do. If we think of 1 over 1 minus x is the sum from k equals 0 to infinity of x to the k, we can use this to find series representations for natural log of 1 minus x and 1 over 1 minus x squared. Now neither one of these involves the three properties we just talked about, where we were adding or subtracting, multiplying by a power of x, or doing a composition. You might be tempted to think the second one kind of looks like a composition, but the composition only applies to where the x is. And I've replaced my entire denominator with something different. So the trick here is to recognize that the integral of 1 over 1 minus x is negative natural log absolute value 1 minus x. So if I can just integrate this power series and throw an extra negative in front of it, then I'll have a power series for natural log of absolute value 1 minus x. So if we integrate the sum from 0 to infinity of x to the k, it's actually going to be really simple, because every single one of these terms, remember, is just a power of x. So even without having all of them written out, we know that every single one of them is going to involve the power rule. So we can just do this symbolically with the k's and say, well, the power rule says the antiderivative for x to any power is going to be add 1 to the power and then divide by the new power. And we're going to write this back in series form, and I'm going to stack it like a fraction. This would be for negative natural log absolute value 1 minus x. We asked for positive natural log of 1 minus x, so the easiest way to get rid of a negative is to multiply by another negative. So natural log of 1 minus x is going to be the negative of k equals 0 to infinity, x to the k plus 1 over k plus 1. The k's in here sometimes make it a little bit confusing because you see another letter, but remember, it's x that's the variable. K just represents some unknown number power. And we're just doing the power rule. Now for 1 over 1 minus x squared, the derivative of 1 over 1 minus x, you could think of this as, if you wanted to bring it up to the numerator with a negative power, is negative of 1 minus x to the negative 2, or negative 1 over 1 minus x squared. So just like in the last case, we've got an extra negative here, and we'll have to account for that when we write our series. But basically all we have to do is take the derivative of our power series and multiply by -1, and we'll have a power series for 1 over 1 minus x squared. So we want this time the derivative for the sum from k equals 0 to infinity of x to the k. Again, it's just the power rule. The only difference is this time we're doing the derivative. So the k is going to come down. For derivatives, old power comes down, and we subtract 1 to get the new power. There's a problem here, though, that often arises with derivatives. The answer has to remain a polynomial. So my index started at 0 for the original. If I use the same exact index and starting point, and I were to plug in k equals 0, the first term would be 0 times x to the -1. And we don't want that. We don't want x to any negative powers. We are going to start this polynomial off with a constant always. So very often with derivatives, we have to adjust the index up 1 to account for the fact that the power just went down 1. And if you look back at the original polynomial and you think about what would happen with this guy if I took the derivative, you would see that the derivative of 1 is 0, the derivative of x is 1, the derivative of x squared is 2x. So the derivative doesn't start off with an x to the -1, it starts off with a constant. It's a constant, then a linear, then a quadratic. So we need the same exact thing to happen in our derivative. So we've got to adjust that, the index. But remember, this was for negative 1 over 1 minus x squared. So positive 1 over 1 minus x squared, we're just going to multiply by -1 to cancel off the negative. So this is the negative of the sum from k equals 1 to infinity of k times x to the k minus 1. So the very last trick I want to show you to finish up 9.2, there's a lot of different ways that we could find just a couple of infinite series and tweak them and multiply them and do composition and change them into completely other series. That way we don't have to constantly be going through that entire process of generating a Taylor polynomial. And there's one more trick that we can do that will be along that same line. And remember back to when we were talking about geometric series, where if you've got the sum from k equals 0 to infinity of a times r to the k, if this is convergent, then it always converges to a over 1 minus r. If you're ever dealing with a function that even in any way resembles this, what we can do is just some clever little algebra to make it match, and then identify the a and the r and create the series that way. So we're going to get our function to match if possible. And there are two key things here that we have to make sure always match. And that is the 1 and the minus. Those are super important. That 1 must always be 1. And then we must always have subtraction. But we just saw a minute ago we had an addition, and we were very easily able to fix that and say minus a negative. So if you're working with a rational function and there is any way possible to get it to match a over 1 minus r, that would be the fastest way to create a series for that function. So we're going to find a geometric power series representation for each of the following. Um, 2 over 1 plus x. Remember, our goal is to get this to say a over 1 minus r. We've got to have a 1 in front, and that is accomplished, and we have to have subtraction. So all we really need to do to fix ours is to change it to minus a negative. So we're going to say 2 over 1 minus negative x. So we've got the 1 and we've got the subtraction. And then we can match them up and say, well, a must be 2 and r must be negative x. And then we can throw these guys into a geometric series. So the sum from 0 to infinity of a times your r to the k. And it's also possible, if you watch some other videos or look at some other examples, very often when there's a negative in here, they like that negative to be by itself. And we did that a few minutes ago. You could always split this up as a negative 1 to the k times x to the k. Really, either one of these is perfectly fine. We're going to do one more real quick. This time I'm going to do 6 over 3 minus x. 6 over 3 minus x. It's kind of similar to the a over 1 minus r. We've got the subtraction. That's good. But we don't have a 1 in the front of the subtraction. So the way that we're going to fix that is divide everything by 3. If we divide everything by 3, 6 divided by 3 is 2. 3 divided by 3 is 1. It stays subtraction. X divided by 3, we can't simplify that, but we do need to write it. And now we've got our 1 and our minus, and we're ready to identify the a as being 2 and the r as being x over 3. So our series for 6 over 3 minus x is the sum from k equals 0 to infinity of a times r to the k. We could also check our interval of convergence on these if we wanted to very easily. Remember, geometric series are only convergent when the r value is less than 1. And we'll multiply that 3 over. That means absolute value of x must be less than 3. So x must be between negative 3 and positive 3. We don't ever want any multiplication or division in here. We could have addition or subtraction. That just means that we have a different center other than 0. But any multiplication or division inside of there will always multiply or divide over to the other side. So that's why we change it into absolute value of x is less than 3. Remember, our goal is absolute value of x minus c is less than r. There is no multiplication or division on the left-hand side of that inequality. It's just going to be addition or subtraction. It's subtraction if your center is positive. It would be addition if your center was negative.